with a bit of an example. So imagine we're the police, and we've got an eyewitness to some crime with us. And we want to get the likeness of the suspect out of that eyewitness. We want to sort of get them to maybe sort of describe that suspect, and we want to generate some sort of sketch of that. And this, unfortunately, turns out not to work very well if we just get them to describe and then generate from that description. So these are actually what DALL-E generated when I tried to describe myself, and it's not really a very good likeness. So kind of what's going wrong here? What's the problem? Well, the problem is not that DALL-E's not capable of generating my likeness. It can generate lots and lots of things. It could definitely generate something that really looks quite like me. The problem is much more, how do we get DALL-E to actually generate something that looks like me? We've got kind of a difficult process of how we control that system and how we kind of get it to produce what we want. What we could do, though, instead, is we could think about kind of showing the eyewitness images, and we could ask for their feedback. So we might sort of show them this image here, and they might tell us that this is pretty terrible. We then might show them a second image. We might use the feedback from the first to choose a second one. And it might then say, well, this one's not good, he's a bit too fat. And then we can keep kind of iterating with this. We can kind of keep choosing new images to show based on the sort of feedback that we've gathered so far, until hopefully we've actually sort of quite well recovered the true likeness of the suspect. So we can kind of learn from this feedback, and we kind of have this much more iterative process. Now, what's actually difficult with this? What's the challenge that underlies this? Well, it's the sort of sequential decision-making process that we're making here. So we have to sort of each time choose kind of what images we need to show based on the sort of feedback that we've gathered so far. So we have a sequential decision-making process, and it's a sequential decision-making process about gathering data. So here, that feedback is data we're gathering on that actual person, and we can view this as a sort of a sequential data-gathering process that we need to control. And the problem is that generally we're not very good at this. So while over the last decade or so we've seen this sort of revolution in machine learning, and with that we've seen this massive improvement in our ability to learn from existing data, we're still really quite bad at these kind of sequential decision-making problems to gather that data in the first place. So what I'm going to be talking about is how can we do that kind of data gathering intelligently? How can we kind of go back and make sure we actually gather good data in the first place? And hopefully the importance of that's pretty clear. If we do any machine learning, it's only going to ever be as good as the data that we've actually gathered to train on. And even beyond machine learning, if we want to do things in the sciences and so forth, that sort of data gathering process is absolutely critical to the success of all these kind of ventures. So what we're going to be looking at is ways to sort of formalize that data gathering process. And then once we formalize it, we can start kind of constructing algorithms to control it. And we're going to be seeing, in particular, how we can use information theory to really do this in kind of an intelligent and adaptive manner. So to do that, what we want to do is give some framework to all of this. And what we can think about is the fact that any data gathering process is essentially an experimental design problem. So there'll be some sort of things we can control while we're gathering that data, and those are going to be the designs of our experiment. So if we can't control anything, there's nothing for us to do. And if we can control things, we can think of those things we can control as these kind of designs. And once we've gathered things, the output for that experiment is the data that we're actually gathering. So to give some examples, we might be looking at how you say set up a clinical trial. We might look at sort of the questions you ask in a survey. We could be doing something more like active learning, where we're choosing sort of which images to label. We could even have kind of physical laboratory experiments. We could have a chemist and how they actually run their actual experiment. And these all fall in the same framework where we've got these decisions that we need to make, and we want to make those decisions that give us the best possible data to come out at the end. So to give a really simple example of where we might do this, imagine we're a psychologist and we're trying to learn about people's subjective value of money. And we might ask them questions like, would you prefer £60 today or £100 in a year? But another question we could ask is, would you prefer £200 a day or £100 in a year? And it's pretty obvious that this sort of first design is a better design than the second one, because in the second one, we're really not going to learn anything from that question, and we've got this sort of intuitive notion that this first one is better than the second one. But let's try and sort of think a bit more carefully about exactly why that's a better design and start moving towards a way we can kind of formalize this and actually start doing some machine learning and things on it. And what we can think about is that second question is bad because we essentially already know the response. So it doesn't matter if we've got someone who's sort of very conservative trying to save, or we've got someone who's maybe has a problem with drug addiction. They're both going to take the money immediately, and we've learned nothing about them from their response. If though we start looking at the second question, £60 a day, £100 in a year, these people are likely to respond differently. We're more uncertain about what's going to be coming out from this, and we've therefore kind of learnt more by seeing that response. So we can start thinking here about formalizing things in terms of kind of this uncertainty and how much we expect to kind of learn from this data that we're going to be gathering. And what we're going to be building up towards is we're going to see that basically this can actually be formalized by something called an information gain, and we're going to be saying that basically good data is data that gives us lots of information. And this doesn't just apply to these kind of really simple examples with very simple questions like this. If you get up ChatGPT and you do something with ChatGPT that's trying to learn about you and try to get it to sort of figure out things like preferences of you, it turns out it's really quite bad. So here it's doing something called the classic 20 questions problem. And it says, I'm thinking of a historical person. Please ask me yes or no questions to figure out who it is. So they first ask, is the person you're thinking of male? And I say no. Then you say, is this person from the 20th century? No. And these are not necessarily crazy questions so far. But as it goes on, it gets kind of quite bad. And so by the 11th question, it's saying, are you this person from the 17th century? No. Did this person live in the 18th century? No. Did this person live in the 21st century? No. All right, they must live in the 20th century. And so what we see is that even when we take some really powerful model like this, and a very simple problem in many ways, it can really fail quite spectacularly. So even with these big models, they're often still very ineffective when it comes to these kind of decision-making problems. So even with ChatGPT, there's a lot of work to do if we actually want it to sort of gather data effectively and ask questions rather than give us answers. Okay, so now that we've kind of motivated, we've got a general idea of what we're trying to do, the key question we need to think about is what actually is good data? If we're trying to gather good data, what is the definition of good data? What is the definition of bad data? And here what I'm going to do is appeal to the actual definition of data itself. So the definition of data is something that conveys information when we interpret it. And that naturally means that we can say, well, good data then should give us lots of information. Bad data should give us less information. And we can start thinking of formalizing the utility of data in terms of the amount of information it's actually going to provide. And to do that, we're going to introduce this Bayesian experimental design framework, this thing that the talk is going to be about. And we'll see that basically Bayesian experimental design is how we formalize the utility of data through the amount of information that it provides. So just to sort of introduce a little bit of notation that we're going to use for this. So we're going to say that we're going to have some designs, chi. So these are the things we could control, all our sort of levers in that data gathering process. We're going to say that the data we get out of it is y. So this is sort of the outcome of our experiment. And we're going to say there's some target variables theta. So this theta is going to be whatever we want to learn about. So it might be the parameters of our model. But it might be other things as well. It might be, say, downstream predictions. So if we're doing active learning, what we really want to learn about is future predictions we're going to make. It could also be something sort of physical. We could have some big model, but there may be some like real physical parameters we're trying to learn about. But whatever it is, we're just going to call it theta. This is just what we're trying to go and learn about. What Bayesian experimental design then says is that we can formalize the information that we're getting from an experiment by using some sort of generative model. So if we've got basically essentially a simulator, and that simulator can generate both y and theta, both the outcomes, the data, and what we're trying to learn about at the same time, Then we're going to be able to use this to formalize the utility of our experiment, and in turn, we're going to be able to use that to optimize our actual design decisions. So these things can take lots of forms. So we've done work where it's kind of old school simulators. So this could have some big climate change simulator. Maybe you have a statistics model. So there's lots of cases of using this in kind of the SRI model, which is where all your R values and beta values come from with COVID modeling. So that's another sort of valid thing you can have here. Or it could just be a machine learning model. It could be a Gaussian process, a stochastic neural network, anything that's probabilistic and is going to be able to generate these things for us. Once we've got this kind of simulated, this kind of model, we can then say that we can actually formalize now this information gain, to be precise. And the information gain is defined as a function of our design decisions and our outcomes, and it is just given by the entropy we have before we run the experiment minus the entropy we have after. So we start essentially with some amount of uncertainty. Remember, theta here is what we're trying to learn about. Entropy is a measure of uncertainty, so this is our uncertainty before, and then we've got minus our uncertainty after. And here, this prior, this posterior, these can be derived from that simulator. Once that simulator is defined, these things themselves are defined, and therefore all of this is well defined for us. So this is now that formalization. This is the utility, essentially, of our experiment, because it's our reduction in our uncertainty in what we cared about. And so hopefully it's clear now why theta is the thing we really want to learn about, because we're talking about our reduction in uncertainty in what we want to learn about. We can't, though, actually use this directly. So this information gain is a function of the data. And the whole point was to try and sort of make good design decisions. So we're trying to figure out a priori, how should I design my experiment to get good data? But at the moment, I've got a utility function that is a function of that data. So what we do instead of working with information gain is we work with simply the expected information gain. So we can take that information gain and we just take an expectation over the possible data we might see. So here, again, we're using our model, our simulator, and we can think about just simulating possible data from it. And then once we simulated that data, we can say, well, how much did we actually learn from that as well? And both of these are derived from our model. So we sort of essentially can use our model twice. We can use our model to simulate the data, and we're going to use the model to sort of formalize that information gain. So here, if we look at it, we've got this expectation of this y given chi. This is essentially just the marginal out of our simulator. We can sort of marginally simulate that data. And then here, again, we've got this reduction in our entropy. We can now just say that, well, given all this, our optimal design is the thing that optimizes this expected information gain. This is the optimal design is the one that gives us the most information in expectation. So this is kind of the information theoretic formalism of the optimality of our experiments. And it's a very old idea, actually. This goes all the way back to sort of the 50s, and is this kind of sort of fundamental formalization of how good an experiment is. There's lots of other ways we can think about this as well that you might have seen differently. So this expected information gain is exactly the same thing as the mutual information between theta and y. So it's the mutual information between our data and what we're trying to learn about. But this gives us a bit more, when we think in terms of expected information gain, it gives us maybe a bit more intuition of why the mutual information is the thing we actually care about in these kind of scenarios. We can also look at it as an expected KL divergence. So we have sort of a KL divergence between a kind of Bayesian posterior and a Bayesian prior. And again, this is the same quantity. And you can also flip that. We can say that it's an expectation over theta and y of the log likelihood minus the log marginal likelihood. In other words, in expectation, how much does knowing theta reduce my uncertainty of my predictions? So if knowing the truth was super informative to this prediction, that actually goes backwards as well. It means both ways. If the knowing theta is informative to y, knowing y is informative to theta, so we can kind of look at this kind of symmetrically both ways. Okay, this is probably a good point to just pause for any questions that anyone has if this hasn't been clear.
Actually, I have one. you mentioned that you're generating data with your model, I think. And I'm actually curious how you generate data with discriminative models, not generative, in the context of learning. And
it's a great question. The answer is you kind of can't. So whereas in machine learning, you've almost always got an analog between a generative approach and a discriminative approach. What this is sort of telling us is that that doesn't hold up when you're gathering new data. You sort of inherently have to have this kind of simulatory process. So you could train a discriminative model to learn that model. So in a sense, when you train, say, a diffusion model, the training process of the diffusion model is kind of like training it as a discriminative model to then be a generative model. But you need something to predict ahead. And if you kind of think about the problem, you can think about the fact this is inherent. We are reasoning about things we don't have. So usually in machine learning, your data is there, and you've got a lot more flexibility about what you can do because you've got data there and you can work with it. Here we're talking about data we don't have. So when I talk about it being Bayesian experimental design, I'm not inherently wanting to be philosophically Bayesian here. I'm actually working from information theory. And because we're reasoning about stuff we don't have, that reasoning is itself this kind of Bayesian notion of uncertainty, this notion of how we're uncertain about things we don't know enough. And so it becomes kind of unavoidable. There really isn't great alternative frameworks to this. You can work with things like Fisher informations, but they basically are only going to work in helping you sort of asymptotically. And so this really is the language, in a sense, of sequential decision making. And this sort of generativeness and this Bayesianness is kind of inherent to the problem, really, rather than actually the approach we're going to take. Yeah.
If we have like probabilistic graphical models, right? How related is this to like the prior predictive check? What's the relationship? Yeah.
I mean, yeah, it's quite linked. I mean, if we look back, you were essentially simulating data from your prior predictive. So before we've seen any data, your prior predictive is your best kind of prediction of data. And sometimes you don't necessarily set these up as Bayesian models. If you're doing active learning, you might train some stochastic neural network, and the prior predictive now becomes sort of simulating from your current stochastic network. And then these other quantities become how you update that stochastic network. So it's always in philosophy working with that. Practically, and I'll come to this maybe a bit more later in the talk, there are other ways we might want to do it. But the formalism is always the prior predictive, in a decision theory sense, is your best predictive distribution for how data will be generated, and that is what we use. And then here, again, you've got this kind of model checking, as you were sort of saying.
Thanks.
Cool. Okay, so at this point, we've got this sort of formalism. We've gone through and we've formalized this notion of the optimality of an experiment, and we've done it through this expected amount of information. And this can be quite useful, but in isolation, often we can make good design decisions ourselves. If we're just making a one-off decision, a lot of the time a human can just sort of sit down and do that. Where things get much more interesting is when we start being adaptive. So when we want to start making sequential decisions, now it's not so viable to just have a human sit down and kind of sequentially make all of those decisions for us. And we have to know how things are going to update and things, and it becomes much more important to have some kind of machine learning based approach. And what's great is that this Bayesian experimental design is very well suited to this as well, because we can essentially just iteratively use the same approach. So if we've got a model, we can go and optimize the expected information gain under that model to make a design decision. Once we've got a design, we can go and gather a new bit of data with that design. So we get a new bit of data and an observation. And then we can just go and update our model. We can give ourselves a new model. So we might do a Bayesian inference, or we might go and retrain our neural network. We can do something to incorporate that new bit of data. And once we've done that, well, we've got a new model. And so the optimality under that new model gives us a new design decision. And so we can just kind of cyclically do this, where we're going to iteratively use our current beliefs, our current model, to make a design decision, gather a new bit of data, update that model, and keep iterating along with that. And what this gives us is what's known as Bayesian adaptive design, which has this terrible acronym that it's actually called BAD. But bad is not actually so bad. We can actually go and use it relatively well. So to go back to sort of look at that kind of psychology experiment example, we might ask first the question, would you prefer £80 today or £100 in 3 months? And maybe this person says they want £80 today. And then we're going to say, well, would you prefer £70 today or £100 in 4 weeks? And here we've chosen less money in a shorter time because they chose that kind of shorter horizon. They wanted the money now, so we're asking a question that's tailored to them. And again, they want the £70 today. So now we ask them, would you like £30 today or £100 in 16 days? And for most people, this would be a silly question. Very few people are going to take the £30 today. But based on this person's behavior, maybe it's not unreasonable. And in this case, they do take the £100 today, and then we get something again, £38 today or £100 in 3 weeks, and they go for £38 today. So we've kind of honed in on them a bit like a detective. We've kind of utilized each sort of response to kind of make each next question sort of more pertinent. And obviously this is a very simple example, but the same principle is going to apply all the way back to that example at the start where we were generating faces from DALL-E. So if we were generating a face from DALL-E, we gather some feedback, we generate a new face. We gather some feedback, generate a new face, and the same exact principles are going to be applying, just doing this at a much bigger scale. And what's particularly useful when we do this with this Bayesian adaptive design approach is we've got a self-similarity in that expected information gain. So in the same way that when you kind of do inference, you can use your posterior at one step as your prior at the next step, the same thing is going to apply here. We can look at what's called the incremental expected information gain. So we can say this is a function of this history ht minus 1. So this is basically everything we've gathered so far. And then we just now take an expectation over the new data, yt, given our new design decision and all the previous data, and then we look at how much our current beliefs, our posterior entropy at t minus 1, minus our entropy at t. So we're looking here with this updated model, and we can do this here in an entirely Bayesian framework. You can also just retrain these models. So instead of working like this, you could just think of, I'm going to retrain my model and then reevaluate this thing again. But whether we're doing that or not, it gives us this framework, this BAD framework. And we can sort of now complete it where we're saying, as I said before, we choose design decision incrementally by, in this case, maximizing this conditional expected information gain on based on the data we've seen so far. We get a new observation, and then we can, for example, update the model using Bayesian inference or potentially by some other mechanism. And this gives us what's called the sort of traditional BAD, or you could also call it the greedy Bayesian adaptive design approach, which we'll come back to later. There's a big problem here, though. Both of these steps are extremely slow, and we're going to kind of go into some detail about why that is in a sec. But in short, this thing is going to be incredibly difficult to do. It's a very horrible optimization. Model updates are usually quite expensive as well. And so this isn't sort of actually that practical a kind of thing for us to work with, because if we actually want to go and run this with a human participant, we can't keep them waiting for 6 hours between those questions. We actually need things to sort of run quite quickly. And so, as I sort of said it before, some of these ideas, they go all the way back to the 50s. They're not very new ideas. But historically, the view has been that this is just kind of a theoretical optimality, but not really a practical way of doing things, because it's just so slow that we have this kind of massive sort of computational elephant in the room that we basically can't ever actually do it. And what actually happens is that in practice, people had only been able to do this in a few dimensions, and we'd only been able to do it for very sort of simple problems. So in the rest of the talk, what we're basically going to go through is why this historical viewpoint is now out of date, and why it's now actually a potentially really exciting algorithm to go use. We're going to go through a series of innovations that have really, really dramatically sort of reduced this kind of computational load that has suddenly made this into what I think is now a much more viable approach that we can actually really start thinking about doing in practical problems. So let's though first think about why is this such a horrible, difficult problem? And the first big issue is that this expected information gain is what's known as doubly intractable. So 99% of the time in machine learning, we're basically dealing with some kind of expectation. We do some sort of, say, stochastic gradient descent to sort of minimize or maximize, minimize some loss or maximize some sort of model probability or something. So we're always kind of basically doing optimization of expectations. But here, you actually don't have an expectation. You have actually an expectation of a function of an expectation. So this posterior here, that's intractable. We need to sort of, we theoretically need infinite compute to get that exactly. And then it turns out the entropy of that is this doubly intractable thing. It's an expectation of a function of an expectation. And then we've got actually also got this outer expectation to deal with as well. So this is probably easiest to see if we kind of rewrite that expected information gain. So we've just actually got the same equation as before, but we've just done Bayes' rule on it. And so we can also say the expected information gain is an expectation under our model, this sort of joint simulator on theta and y, of the log likelihood over the marginal likelihood. So this is how our predictive model, given what we're learning about, over our marginal predictive model. And once we look at this, what we can see is that py given chi, that is generally intractable. That is an expectation over theta. So we've got an expectation of the outside of a log and then an expectation inside. And you can't just move that through. It's basically Jensen's inequality tells you that this is going to be biased, and therefore you can't just sort of work with samples on the outside. And if we then say naively just do a Monte Carlo estimate for this, so we're just going to draw some samples from the outside. We're just going to draw these yn, theta n from our simulator. Then we'll take an average for the outer expectation. What we see is that each term in our expectation is itself intractable. So the likelihood's fine. This term is generally fine. But this marginal likelihood is nasty. We actually can't evaluate this. But what's more is each one of them is different. It's not one intractable thing that if we get, we're done. We've got n, capital N intractable things. So the more samples I take on the outside, the more intractable problems I make for myself. And so this is going to be an incredibly nasty sort of setup that's much, much worse than we're used to dealing with in a machine learning context. So the simple thing we might do is we might say, well, let's go and do Monte Carlo for that as well. So we could draw, say, some theta m dash from p theta, and we can make a second Monte Carlo estimate inside here. But now we start to see sort of where the problems are really coming in. So the cost of this guy is now scaling as n times m. We've got this sort of product of these. So each time we draw more outer samples, we're having to make more and more of these inner samples. And if you sort of, so what we can say is basically the total budget here is equal to m times n. And it turns out the optimal thing to do is to set m proportional to square root n. And if you set m proportional to square root n, this gives you a convergence rate of t to minus a third. So most of you probably won't care about convergence rates, but the thing that matters is that this is much slower than Monte Carlo. So if you're Monte Carlo, which we're used to doing, we're always doing when we do stochastic gradient descent and things, that is converging at a much faster rate than this thing will, and therefore this thing is really going to be quite awful for us to actually work with. So if we want to do any of this, the first thing we need to do is we need to somehow get around this nesting problem. We need to find some way that we can actually efficiently work with this, and we can see that just sort of standard Monte Carlo is not going to cut it. And to do that, we can first think about, okay, at a fundamental level, kind of, in what way is this being inefficient? Is there something that we're missing here that could make this a bit better? And what we can think about is that, well, if we do this thing here, each time there's a yn, we're basically making a new estimator. Even if we could share these samples, but even if we share them, we're essentially making a new estimator by taking this average. But if we go and plot that, if we plot y, and then we plot the thing we're estimating, we get these sort of red points here. And then it starts to become obvious about how we might actually solve this problem. There is actually going to generally be some smoothness here. This is actually, in essence, a regression problem, or you could also view it as a density estimation problem, a conditional density estimation problem. So what we could think about is instead of each of these x's being estimated from scratch, why don't we start thinking of actually learning some kind of regressor? And if we can learn the regressor, then we can share information between these. They can start learning together, and maybe this thing's going to start becoming a bit more efficient. So what we could do is we could say, well, if we could learn, say, some approximation, so we're going to take that sort of marginal likelihood, we're going to introduce this functional approximation that can approximate at any point, and then we're just going to stick that straight in to our estimator. And what we've now got is something where our cost is additive. So there is some cost to learn that approximation, and then once we've learned that approximation, there's some cost doing this estimation. So if we now, say, use a budget of m for this first bit, the cost is going to be m plus n rather than m times n, and this is suddenly actually going to get fundamentally much more efficient. And what's even better is it turns out when you do this, you automatically get a variational bound. So this estimator here is actually an upper bound on the expected information gain. It's always an upper bound. Moreover, it's an upper bound that becomes tight. So if this actually approximation becomes exact, we're going to re-recover the proper expected information gain. So it's not a variational bound like we're used to seeing in, say, a VAE or something else, but it is going to behave the same way. It's going to be something where it's always greater, and as it optimizes, then it's going to get tighter. So the key is this ability to get tight. So if, for example, we minimize this with respect to phi, the minimum of this over phi is going to be the expected information gain. So we've now suddenly got a way where we kind of switched our estimation problem to an optimization problem. If we now think about optimizing in phi, that is going to give us our kind of estimation to work with. And in particular, there's actually going to be a whole host of bounds it turns out you can use. So this is something we call the marginal bound, but there are lots of other ones as well. So one is called the Barber-Agakoff bound, and here we're going to use a different form of the EIG, and this time we're going to introduce some amortized approximation of the posterior. So this is basically now the same thing as an encoder in a VAE, so if we stick in an encoder in our VAE, this time we get actually a lower bound. In fact, even if we work kind of with the NMC estimators, there are ways of kind of making variational bounds out of them. So if we use instead now an importance sampling estimator for the marginal likelihood, it turns out this whole thing becomes a variational bound itself, and it's a variational upper bound where the variational thing is the proposal that we're using in that inner estimator. And you can even go even better. You can actually include m equals 0 in here, so you can share a sample. So here there's one sort of theta that's been used for the likelihood, and if you stick that into your estimator here, you can actually switch this from being an upper bound to a lower bound, which makes it even better, because now we can start sandwiching it. And it turns out through this you can recover a lot of things that you see in representation learning for mutual information. So if you've come across info NCE, for example, as a mechanism for doing representation learning, info NCE is actually a version of this with a particular proposal. So all, more generally, any kind of contrastive learning, any sort of contrastive representation learning approaches, implicitly they're actually under the hood working in the kind of same way as all of these things are here. And if we now sort of think about this, just to give a bit more detail, what we have is something where the gap is again going to sort of look like a kind of a KL divergence. So the gap for each of these is a bit different, but the key thing is that all of these behave like other variational bounds. As we get better at our approximation, so our approximation here, it was to the posterior. As that get closer, then this variational bound is getting closer and closer to the EIG. And if we then go and look and sort of say, well, how does this actually work? Well, we've got this key thing I said before. We've got the cost of training the variational approximation plus the cost of the estimation afterwards. So we've got this additive cost, and we can now think about sort of spending some time training that variational approximation. Once it's trained, then we can do some sampling to do the expectation, and we can get these big improvements of sort of multiples of magnitude in kind of how effective that's going to be. Where things, and what this will also now give us is a fundamental improvement in convergence rate. So this nested Monte Carlo we had before was order t to the minus a third, and we can actually, with these variational approaches, get back to this sort of order t to the minus a half. So t to the minus a half, that's what stochastic gradient ascent goes at. That is what Monte Carlo goes at. So we're back to the rates that we're kind of used to. So what we see here is that this is not the normal trade-off between Monte Carlo and variational inference. We actually now have these variational approaches are fundamentally better than these Monte Carlo approaches. They are lower bias, they are lower variance, and they're just going to work substantially better. But there's still a big issue to kind of deal with here. So even though these things are sort of doing much better, we weren't trying to estimate in the first place. We were actually trying to optimize this expected information gain. And again, the variational things are going to come to our rescue here, and it's going to get even better, because what we can now think about doing is if we've got a variational bound, well, actually, I can now do simultaneous optimization. So in particular, the maximum of my expected information gain over designs is equal to the maximum of a variational bound over designs and variational parameters, as long as I use a lower bound. So we had different bounds, some were upper bounds, some were lower bounds. As long as we choose one that's a lower bound, and we have a sufficiently kind of flexible variational approximation, then we can actually now do our optimization in this joint space. And this is now singly intractable. This is something we can go and do stochastic gradient ascent on. So we've got something where now if we simultaneously update our designs and update our variational parameters at the same time, we can go and we can do our normal deep learning training schemes. We can do everything we would do normally, and this is going to converge much quicker. So essentially, by taking this original problem and lifting it in some sense to this higher dimensional optimization space, we've got around this double intractability, and we've now got this mechanism to sort of train things really effectively. And it's quite analogous to sort of what's happening here as to what would happen in a variational autoencoder. So we can kind of think about this as simultaneously you're kind of training your encoder process and your decoder process at the same time. But in some ways, it's actually even better because that encoder doesn't necessarily need to always be a conditional distribution. Some of these can actually be just fixed distributions that don't depend on the input. And the design doesn't necessarily need to be a whole large neural network. So we've, again, got the same principle of co-optimization of these things, but it can actually be even easier than that scenario. So what we're seeing here is this real power of this variational approach is not only that we're sort of now sidestepping that double intractability, we're also managing with this to do things as stochastic gradient methods. We've got this unified approach where we're going to be able to just sort of train everything as one big stochastic gradient ascent, and that is going to massively change things like the scaling. So here, we can now start doing things in much higher dimensions than it used to. So as I said, historically, people would maybe only do this up to about 4 or 5 dimensions. But this variational approach, this is going to start working in hundreds of dimensions, maybe even higher. And it's going to get really quite big gains. So these top 3, these are all approaches using the variational approach. Because it's nested, you can't usually directly estimate it. So this is an upper and a lower bound on the true value. And we see at the bottom that it's much bigger than the information we gain on the other things. And appreciate here that information lives on a sort of a logarithmic space. So this is kind of, this isn't really sort of twice as good. This is, in a sense, this is more, it should be thought of as kind of sort of 4 or 5 orders of magnitude bigger because these things live in this sort of logarithmically increasing space. So through this, we're managing to sort of massively improve the scaling with this and we're going to make sure that we can run things much quicker as well. Okay, this is probably another good point to pause for any questions, if anyone has anything.
Okay, so I do have a question because I somehow lost the link between the setup of the parameters of the experiment and what they represent. For example, in your example with this LLM, does it represent do you assume that you parameterize experiment with some parameters that you optimize over? So it can be, I don't know, the LLM temperature or something of this nature, or what is this parameter that I don't remember the
chi.
The chi, yeah, exactly. So what could it be?
Yeah, sure. It's a good question. So it could be lots and lots of different things. I've kind of avoided specifying it because it's whatever you can control at the end of the day. So I'll explain it a bit more directly as well, but the starting point is anything you're making a decision on, you're optimizing for. And what that will be will vary hugely depending on context. So say we're doing this in an LLM and we want to get the best question. You might then actually have it as the tokens in the space, and then you want to optimize the tokens. But you'll probably do it in the embedding space so that it's continuous. And you could then optimize in that embedding space to get the best token to work with. If you were doing, say, active learning, it might be the input. You're going to optimize the input that you look at. If it's if it was, say, the experiment with the psychologist, we'd optimize the amounts of money we're offering and the delays, and those would be our parameters. So it's whatever is the kind of core decisions, and that will vary hugely on context. And the obvious downside with a lot of this is that it has to be continuous. So that we're doing gradient-based methods, and what we're losing by this is that it's going to be more difficult to do for discrete design decisions.
Okay, and this also comment about discrete and continuous was also something that was missing. So thank you very much.
Any other questions? Okay. So far we've come through. We've done this work to sort of give us much better sort of estimators, and in particular much better optimization scheme. So let's go back and think about our example. So we ask our person a question: would you prefer £90 a day, £100 in a year? They say they want £100 in a year, and we say, great, okay, I'm going to run, it's just a single stochastic gradient optimization now. It's really efficient. It's much better than what we had before. But, it's still going to be 20 minutes. I'm still training something. I'm still, got to actually go and do this optimization. It's not going to happen instantaneously. And maybe for this problem, it wouldn't be 20 minutes because it's so easy. But if we're, say, working with stuff in a much sort of higher dimensions, with the police sketches, it's going to be much more difficult. So now we need to sort of find some way to remove all of that computation from the experiment itself. We need to actually find some way where we don't have to do this expensive fitting of the posterior. We don't have to do the expensive optimization over that design space, because if we actually want to run things, we really do not have time for us to actually go and run this. And in short, we need some way we can actually run this in real time. We need to basically remove all of this computation from the experiment if we want to do it in a lot of real scenarios. And to do this, what we're actually going to do is we're going to go back to that Bayesian adaptive pipeline itself, and we're going to actually reinvent it. So remember, from before we had this idea that we'd optimize the IG based on a given model to choose a design. We'd run an iteration of the experiment, and then we'd update our model based on that new observation. And what we're now going to do is we're going to basically strip that model out. We're going to try and replace that model with just some deep neural network that is just going to make those design decisions directly for us. In particular, we're going to want something that's taking in all the stuff we've seen so far and is just going to spit out each next design decision that we're going to try and make. And it's going to turn out, actually, we can do this. And the reason we can do this is it will turn out that the sort of the optimality of that network is actually dictated up front. We don't actually need to see the data to know how that thing is optimal. So to sort of understand that, let's think about what it's going to look like and how it actually has to behave. So it's going to basically be some deep neural network. We're going to call it a policy network. And it's taking in all the data we've gathered so far. And its job is to return the next design decision. So this is essentially kind of like a regression. We're sort of regressing from this data we've gathered to our design decisions. But the data then is kind of just the input to this process. It's the point at which we're making that decision. So it's not needed to actually figure out its optimality. It's actually the model itself that was originally dictating what is optimal in this sequential decision process. So this thing can actually be completely trained up front. And this gives us something that we call deep adaptive design, or DAD for short. And the simple idea is that we're going to take that model, we're going to use that model to train this deep neural network. And once we've trained it, we can just use it in the experiment. We can deploy it in real time, and it can make these design decisions for us automatically. And the reason we can do this is that if we go back and we think about what the objective was, this expected information gain, and now we say, well, actually, we want to maximize that across the steps. We want to get the most information across all our iterations. This is just equal to the expected information gain from the whole data set. So we can look at the expectation over all the data I generated of my uncertainty when I started minus the uncertainty at the end. And so this is just a function of our model. This optimality criterion only depends on our model and our decision-making process. So it's a function of this policy, and it's a function of our model. So we can go and we can actually use those same variational bounds from before, and then using those variational bounds, we can go and train that neural network up front before we've actually started the process. So let's have a quick go for an example to sort of see how that's going to look. So we're going to be working with a kind of location finding problem. So we have these two sources. So theta here are the locations that we're trying to find. So maybe it's like a search and rescue style problem. And what we're going to do is we're going to be able to sort of measure the signal strength. And by measuring the signal strength at different points, we want to find those locations. So to do this, the first thing we're going to do is simulate a ground truth. So remember, we're doing this before the actual experiment. So we're going to simulate a possible ground truth for what we're trying to learn about theta. Then we're going to use our currently untrained policy network to make a design decision. So here, that's going to be a location, and we're going to try and measure the signal strength of the source at that location. Then again, we'll go back to our model, and this time we'll simulate the strength of that signal. We'll use our model to simulate the possible outcome we might see. So remember, our model was the simulator for outcomes, and we're going to simulate a possible outcome. So here, the signal strength is very low. And then we've got our first sort of simulated data point. We've got an input and a strength, and we're going to put that back into our network, and that'll give us a new design decision, and maybe it gives us this point here. And then we're just going to keep going with this until eventually we've simulated a whole data set. So we've used this policy network to simulate a data set, and then we can evaluate some loss. We can use, say, those variational bounds to estimate some kind of loss on how much information is in the data we've generated. So we're basically going to simulate a data, and then we're going to look at how much information is in that data. And now it's just a question of simply back-propagating through the system. So we want to train that policy network, and we just have to back-propagate backwards through this system. And so over time, by back-propagating, we're going to be updating this policy network, and it's going to get better over time. So now, after a few steps, it's maybe going to start going towards one of the sources, and then it starts to find it, and then over time, eventually, it's maybe finding both of the source signals. So by doing this sort of back propagation, we've eventually kind of learned this network. And then when we come to deploy it, we no longer need our model. We just use this policy network to make a design decision. We run an actual iteration of the experiment. We pass the actual data back into the network, and then we can actually do this actually in deployment. And what's great is that not only does it turn out that this thing massively reduces the deployment time, so these are real numbers from this problem. It used to take about 2.5 hours. Now it's about 5 milliseconds. It also turns out this massively improves performance as well. So you would expect that this thing of doing it all up front, you would assume from this amortization, we're losing a lot with all of this, but what's actually happening is that it's actually improving the performance. And there's kind of two key reasons for this. The first is we're sort of sidestepping all that intermediate inference. We're kind of doing this deep learning end-to-end thing, and that turns out to sort of help. And also we're learning these sort of non-greedy strategies as well that manage to sort of plan ahead. So by learning these networks, what we find is it manifests a way to kind of plan ahead, plan these decisions, and then roll them all the way back to do things effectively. So I'm running out of time a bit, so I'm just going to very skip through the last few bits. But I just wanted to sort of talk about very quickly about what some of the main sort of big bottlenecks here are. So we've found that this sort of DAD approach has solved this big issue of doing things in real time, and it's doing a big improvement in performance at the same time. So what's kind of left, and how to do things. So the first thing is that it's really time to start applying these things. So the sort of big takeaway I want to do from the talk is that these are really these powerful principled methods, and historically we've not been able to use them, but now we can start thinking of doing them on big problems. We can start thinking of doing this sort of sketch style problem. We can start thinking of simulating things from stuff like DALL-E, get people, for example, to choose these and feed them back. We're also doing things in sort of, say, large-scale climate simulations, in working with large language models to actually get them have good questions, to do things like protein discovery and things. So if we want to kind of do molecular property prediction, we can use all of these things in active learning frameworks to do things effectively. We can also do things like clinical trials, and all these things is there as well. So I think there's a really exciting sort of area where we can now really start to think about using this and doing it in some real problems. So just to sort of wrap things up, because I'm out of time, we've gone through this idea of Bayesian experimental design, this information theoretic formalism to design of experiments to gathering data. And we've seen how if we've got some sort of generative process for an experiment, we can use that to formalize the information we get from data and therefore optimize any design decisions we're making when we gather it. We've secondly got this key idea of doing that adaptively, so we can have this system that can feed back into itself, utilize it, can learn as it goes, and guide future experiment iterations from the information it's already gathered as it goes. We then went through how we had this big sort of computational bottleneck. We had this sort of double interactability. But now there are these variational approaches that allow us to sort of get around all of that and let us do things much more scalably and much more efficiently. And if we want to run things in real time, we've also got this ability to go and use these policy-based approaches that actually remove all the computation from the experiment and therefore just run things almost instantaneously at actual deployment time. With that, it just leaves me to thank you very much for listening and to thank my wonderful co-authors for their help. If you're interested in learning more, we wrote a review paper in this area earlier this year, so that'll be my sort of where I'd point you to sort of learn things a bit more and go in a bit more depth with this. But thanks, and hopefully there's still time for a few questions.